Great question. Does anyone not know what Gesundheit means? Because I say it a lot and I get a lot of weird looks sometimes. It's used as bless you in German. I think if you literally translated it, it would mean good health. But yes. How's everybody doing today? Okay, any major issues starting off the semester so far? Things are going well for everybody. Work with my schedule is I don't have any lectures on Monday or Wednesday, so it feels like Tuesday to me for some reason. I can't quite shake it. Anyway, I guess feeling like the weekend comes faster is better than feeling like the weekend comes slower. So, this is the second of your 2 lectures this week, so I won't see you again until next Tuesday after this one. As a reminder, there are no labs this week, but there will be labs next week. So starting next Tuesday, you start reporting to your assigned lab time. We're going to be starting off slowly though. We're just going to begin on some introductory math review before we get into more of the actual experiments with the stuff that we'll be learning in the coming weeks. But do start getting in the habit next week of coming to your assigned lab time if you're able to make it in person. If you're not with us in person yet, that's fine. Just watch the recordings and contact me about labs. Any questions before we begin for today? Okay. Couple minor things. Make sure you're able to access the Brightspace classroom. If you've been with the school before, it's what we're using instead of Moodle now. And make sure you're able to sign up for your Sapling Learning account. Now, I've been made aware of a small bug when making your account. When you make an account with the website, you have to tell them what school you're with. And if you type in Presbyterian College, it doesn't have that in its quick autofill database. So when you start typing into school name, you hit the P button, it brings up every school with the P. But if you keep typing Presbyterian, it doesn't have that in that particular database. But it doesn't matter what school you list when you make your account. So if you still haven't made your account yet, and if you encounter an issue with that, it's okay. You can just type Presbyterian College. It doesn't matter if you click one of the autofill options. When you're making your account, the school that you list doesn't really matter. Once the account is made, then you sign up for a class, and then you search for class at Presbyterian College, Phys1000, fall 2020, Mr. Hoffbaum. Yes?
That's all on Brightspace, right? Like the link for that to like sign up?
Yes.
All right.
Yes, there's a link to that website in the email I sent to everybody, and I put the same post on the Brightspace page. Actually,
I'm trying to find it on Brightspace.
now let me pull Brightspace up for you guys and show you. Right? Okay, so Brightspace is new to a lot of people. I'm still figuring out everything it can do. But if you log into the Brightspace page, we've separated everything into topics that, oh wait, is this, yeah, everything is, oh, hold on. It might have been some tomfoolery. Okay, no, we're fine. So, back up real quick. On the Brightspace page, this is the page for the class, and we have our different chapters and things down here. Right now, pay only very close attention to this one. I'm still tweaking and modifying the other chapters for the rest of the semester. If you go into Introductions and Resources, now, if you click on just this header part right here, it takes you to, this is just a copy of the email I sent out to everybody. And this link takes you to the Macmillan and Sapling website where you're able to log in or register for your Sapling Learning account. I already signed in, so it'll just take me back to my home page. This is just a link to the Brightspace page that you're already looking at. This is an identical copy of the email that you all should have received on Monday before we started meeting for class. And all of these tiles right here, if you just click on the tile, you will see the sort of an introductory little blurb there. And for the first tile, that's where I put these intro instructions. Every tile after that, I'm going to be listing links to the video lectures in the actual blurb. So because of my camera hiccup, I didn't actually get a recording of the H lecture on Tuesday. Instead, I only have the E lecture. So if you guys need to rewatch the lecture that you guys attended, you can just watch this one. It's the same material. It's just the class is just about 25 minutes shorter. I am currently recording this one, so it will go up starting in page listings. So for every week, every chapter, I'll be listing the links to the videos here. You can come to them anytime for any reason. And eventually I will be adding, subcategories to each one. So in the introductory tab, we've got a sub-file for the syllabus. You can find it here anytime. There's also a rough draft of our formula sheet. It's just every single formula for the entire class. It does need some editing, I realize. I just want to make sure you had some copy of them as quickly as possible. And it's okay if you don't recognize all these yet. This is everything for the whole semester in one document. We're beginning up here, and we'll work our way down slowly. And I will be further editing this document and making sure there's a nice, clean, legible one for you guys looking into the semester. And we'll go through all of these formulas one by one in the lecture. This is just where you can find all of them if you need them. And each chapter will have other documents as needed, like individual assignments outside of, say, if I need to give a remote virtual lab, I'll probably put the lab document in here, or any sort of formula sheet, a constant list, anything listed for each chapter will be in there. I am still modifying all of the names because some of these were imported from the previous section of my class, so I'm tweaking some formatting. Right now, these are the only two, Introductions and Resources in Unit 1. Those are the two that are currently formatted for this particular section of this class. So that's where all the basic information is for right now. And this, if you haven't accessed it yet, if you go here, this link will take you to that page. Does that answer the question?
Yes, sir.
Okay, cool. Anything else? Okay. Yeah, so when you're making your account, the school you list in the account making process doesn't really matter. When you're signing up for the class, that is when you have to search specifically for PC. Any other questions before we work on further content today? Okay. So please interrupt me with questions at any time. We already went over these slides, but we're just starting on something we already, just a little bit of review. So we talked about the scientific method and the steps contained therein. In order to do science, you have to follow these steps. First step is to make an observation and ask a question. Perform research to see if your question has been answered. If it hasn't, form your own hypothesis. And a good hypothesis needs to list the initial conditions. design an experiment to test your hypothesis, you need to collect data, actual measured data, as a part of this experiment. If your data, if your results don't support your hypothesis, you redo your experiment. If it does, you move on and you share your findings. If other scientists agree with you, then your hypothesis might be known as a theory. If after a very long time, a lot of people believe your theory, it might become a law. Are the laws of physics an actual fundamental truth? No. Say it again?
No, I was just saying the start of theories.
Right. All laws of physics that a human wrote down begin as a hypothesis in the human's head. They're produced by humans, they're inherently flawed, we make them better as our understanding improves. They are our best guess at the nature of the universe. What is true is your data. The collecting data is going to be very important. And so it's important to take time during lab to make sure you get good data. If you're rushing through the data collection process, you might make a mistake, and if that uniquely might mess up the rest of your lab more so than anything else. The data is the only thing that we know for certain is true because it's what we measured directly. Everything else is an interpretation of that data. Now, most sciences are roughly divided into two separate categories. Physics is by and large an operational science. And an operational science is one that uses the scientific method completely, and you have to list your initial conditions as part of your experiment and your question. Again, when Newton watched the apple fall out of the tree, he had to list as part of his research, the apple started here, it ended down there. And then his experiments were, if the apple begins at this height and it falls down to the ground, how long does it take? What is its rate of acceleration? How can I mathematically quantify this? If Newton didn't see it fall, if he just saw the apple on the ground, he didn't know the initial conditions and he couldn't run an experiment based on where it came from. So in operational science, you know the initial conditions and you're able to repeat that process in order to actually figure out what happened there. Since you know the beginning and you know the ending, you can compare them as you measure how you got there. The other type is a historical science. And a historical science is one where you don't know the initial conditions. Say Newton just found the apple on the ground. He didn't watch it fall, all he did was find it on the floor. In that case, since he doesn't know where it started, he cannot say with 100% certainty, you know, I did this experiment where I held the apple up here and it fell down. I don't know that it was up here, I just know that if it did start up here, this is a plausible answer for it. But the apple could have started from higher up, it could have been dropped out of someone's pocket, it could have always been there, for all we really know. In historical science, you don't know the initial conditions, therefore you cannot actually say for certain. If I back up to the actual steps here, as a part of your hypothesis, if you don't know the initial conditions, you don't really have a hypothesis and you can't perform an actual experiment for the question in particular. You can perform an experiment to see if something could have happened, but if you don't know where it started, then you can't completely replicate what actually happened. You're guessing. Therefore, historical sciences never leave the hypothesis stage, and they can't actually use the rest of the scientific method. An example of historical science is archaeology and paleontology. They find things in the ground. They can think about logically what are all the ways this could have wound up here, but they don't know the true starting point, so they can never say for certain. Any experiments they do is just guessing to see if something could get into the ground like this, but they don't know if that object followed that exact path. So physics is an operational science as long as you know your initial conditions. Archaeology, paleontology, even meteorology, predicting the weather, is a historical science because you don't really know the initial conditions of the weather all over the planet. You don't know how the weather's going to end up. You're still predicting something. So every single science is one of the two, and only operational sciences actually can use the scientific method to the fullest. So we're going to be doing most of our experiments from the perspective of an operational science. You know the initial conditions and measure data as you get from the initial to the final. And that's how we're going to be utilizing the scientific method. Now, in order to record data, you actually need to be able to take measurements and start working with some numbers. And in order to measure something, you need to know what unit you're measuring it in. So now, we're going to break back into everyone's favorite, the metric system. So these are our metric prefixes, and this class is going to be using metric units because science likes metric units on account of the fact that everything is sort of spaced by increments of 10 apart. Now, in the United States, we like to use the imperial system for a lot of measurements. I have some very common imperial units written up here. We very often measure distance in feet. There's a certain number of inches per foot. There's a certain number of feet per yards. A certain number of feet per mile. These are all common imperial units that we might use here in the United States. They're all specifically units of length. So they're all measuring the same thing. 1 mile is 1,500 something feet. So you can translate miles into feet. You can figure out how many inches are in a mile if you wanted to. And so these are all units of length. Meanwhile, common metric units of length, instead of feet, we have sort of as our baseline meters, the unit that the metric system is named for. And meters is going to be sort of our standard for length and distance in this particular class. I have over here, this is actually a 2-meter stick. This is 2 meters long, which conveniently is a little over 6 feet, so it's pretty useful for spacing people out these days. So this is 2 meters long, and that means that from my hands to the end of the stick is 1 meter. So we're going to be measuring a lot of things in terms of this for the rest of the class. So, metric units of length, we have meters, and from there we can use centimeters if we're talking about something small, or kilometers if we're talking about something big. And is everyone's familiar with how to use and translate between metric prefixes, I hope? Okay. I got some yeses and some nodding. Is anyone not familiar with metric prefixes? Okay. So, say we have our 1 meter here. Actually, this stick is 2 meters, so let's just use 2 meters. This is 2 meters long. Based on our table and our little mnemonic device up here, does anyone know the actual saying that you use to remember what order the metric prefixes go in?
King Henry died in chocolate milk.
Correct. Base in the middle represents the standard unit, so that's not a prefix, it's just where regular meters lives. I usually say King Henry died by drinking chocolate milk, but I suppose you could just drop the by out if you wanted to. I keep it there to remember that's where the standard unit goes. So, meters lives here. Now, this is 2 meters long, so how many centimeters long is it?
200.
200, very good. I'll put this one up on the other side. We have 2 meters. In order to go from meters to centimeters, we start at base, and we have to drag over 2 times. So once from base to decimeters, this lowercase d is deci, and then from deci, one more over to centi. So we jumped over 2 times. That means we have to drag our decimal point over 2 times. So 1, 2. (200 centimeters in 2 meters. If you are going from meters to centimeters, there's always going to be more centimeters in 1 meter. Meanwhile, let's say we're going from meters to kilometers. So how many kilometers are there in 2 meters? Say again?
0.02. No, wait, I can't know.
It's okay. So now we're going to the left. We're looking at bigger things. So we have to go from base to deca. This is deca meters. Lowercase is deci. This is deca. So 1, 2, 3. Moving over 3 times. So 1, 2, 3. So this number is 1,000 times smaller. Meters are 1,000 times smaller than kilometers. So 2 meters in 0.002 kilometers. Again, kilometers are very big. So this is a very small fragment of that conversion. If you're getting stuck on a conversion process, it helps sometimes to just pause and think which of the two is the bigger unit, how many, if I'm going from bigger to smaller, what logically should it be? Don't just convert blindly. It helps to pause and think about it for a second. Excuse me. Because if you did do it backwards and say, for instance, you said that there was 2,000 meters, 2,000 kilometers in 1 meter, just pause as you write that answer down and think that doesn't make any sense. You don't fit 2,000 kilometers into a single meter. So, these are straight, sometimes these are deceptively simple. It's okay to pause and think about them for a second. So, these are our prefixes. I realize I like to use capital letters to help separate deca from deci, but I'm realizing now this table uses DA instead. Out of all of these, that chart over there only encompasses these right here, and these are by far the most common ones. But even out of these, you're never realistically going to use deci, deca, or hecto. Those never really come up very often. It is good to know that they exist. But for this part of the table, everything is intervals of 10 apart from one another. Everything past kilo upwards, instead of jumping by 10, you're jumping by sets of 1,000. So 1 megameter has 1,000 kilometers in it, and 1 gigameter has 1,000 megameters in it. Notice here, we go from 10 to the 3rd, to 10 to the 6th, and 10 to the 9th. This chart can be made available for future conversions. I'm under the impression we just don't have names for things between kilo and mega. There's no name for 10 to the 3rd, 10 to the 4th, or 10 to the 5th. We just jump straight between those two. Any questions so far? Okay. You can put these prefixes on anything, actually. Now, there's sort of 3 standard metric units that are made to go with this system. So the other base units are grams for mass and liters for volume. What is the first imperial unit of volume you can think of?
Gallons?
Gallons. Gallons is a measure of volume. And volume is a measure of how much physical 3-dimensional space something takes up. So a gallon is a predetermined size of coordinates between the x-axis, the y-axis, and the z-axis that takes up so much physical space in the universe. Every gallon of water will have the same size as another gallon of water. So a gallon takes up space. You're measuring depth, width, and height together at once in combination with one another. Volume measures 3D space. You live in a 3-dimensional universe. Length only measures one axis at a time. So length is just forwards and back between 2 objects. Volume is how much 3D space in all 3 axes something takes up. Other imperial units of volume include cups, ounces, things to that extent.
whenever you measure a cup of something when you're cooking, you are measuring the volume it takes up when you mix it into something else. And the reason I really prefer metric over imperial for volume specifically is I can never remember how many cups are in an ounce or ounces in a gallon. They go in sets of like 4 or 6 or 12, and I just get very confused. I have to have a chart on my fridge to remind me how to convert between all those things. But in metric, it's just liters, milliliters, kiloliters, things like that. There is another unit of volume that might come up, and that is going to be things like meters cubed, because, again, volume is 3D space. Whoops. I should have just brought 1 meter stick in here. I should really keep one of those on hand. So, since volume is 3D space, you can take the one-dimensional length in each axis and multiply them together to get the 3D volume. Kind of like you multiply 2 1D planes to get surface area. You can multiply 3 3D planes to get, 3 1D planes to get volume. So meters times meters times meters is also a measure of volume. Our metric unit for mass is grams. That just tells you how much physical matter is inside of an object. So I have a mass of about 1,000 kilograms. That just tells you the amount of physical stuff inside of me. Can you think of an imperial unit of mass? There really isn't one. In the US, we tend to think of things more in terms of their weight, but technically weight and mass are measures of 2 separate things. Mass is the matter in an object, weight is the force of gravity on an object. We'll talk more about that distinction when we get into forces, but the important thing to note is that grams measures mass, okay? So, a couple of quick sample questions using these conversions then. Just take a second and you can talk amongst yourselves or just write it down by yourself if you want to. Just very quickly, what are each of these converted? All right, so how many kilometers is 10 meters?
1.21.
Which one is 0?
All right, good. So if we start from 10 meters, we have to go 1, 2, 3 to the left. So 1, 2, 3. That, the best scientific form is usually to do 0.0. It sort of makes the decimal point a little more visible in my opinion. So oftentimes I will add a 0 in front of my decimal points just to make them a little more present. But yes, we start at 10, we move our decimal point 3 over, and that's going to give us 0.01 kilometers. Next, we're going from centigrams to kilograms. So we start here, 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. So that's 0.001 kilograms. And last but not least, 1,000 kiloliters into milliliters. Now, we're going from a big unit to a small unit. That means the number is going to get bigger. There's a lot more small things inside a big thing than big things inside of a small thing. So, we're going from 1, 2, 3, 4, 5, 6, 7. Yes, 7 over. That means we're going to add 7 zeros. So this number is actually pretty huge. 3, 4, 5, 6, wait. 1, 2, 3, 4, 5, 6, 7. So that's 10 billion milliliters. So we're going to be doing conversions like this all throughout the semester. We're going to keep doing them, keep practicing them. As long as if you need to draw this every single time, you can. It is fine. I'm going to show you a different method of conversion in a second, which also works just fine. Whatever method that best helps you to be able to convert between units is fine. It doesn't have to be the way that I write things down. As long as it is a method and I can read it on the work, it'll be fine. I'm going to show you a different style in a second when we're converting between different units. First though, any questions about these? Okay. We're going to do some other conversions really quickly before we, and I think after these we'll take a quick break. So, these conversions are not metric prefix conversions. These are conversions between different units. Now, you can create any unit you want as long as you define it in terms of another unit for that particular measure. So these are all units of length, 1 inch, there's 12 inches in 1 foot, 3 feet in 1 yard. As long as you have a conversion factor between your new unit and your old unit, you can really make any unit you want. And what we're going to do now is just practice converting between different units that aren't just metric prefixes of one another. This is partially just to show you my method of conversion, because I know it's a little different to how some people do it. We're going to start with seconds in a day. So, our beginning variable is 1 day. This is a measure of time. We have specific measurements of how long a day is. And what I do to convert is, I begin multiplying and dividing by each of my conversion factors in sort of a train setup. So, how many hours are in 1 day? Very good. So, our conversion is 24 hours in 1 day. These two things equal one another. They're the same thing. Which means what I can do is, if I divide this side by 1 day, so I basically just took 1 day and moved it over here. 24 hours divided by 1 day is just equal to 1. Because these two things are the same thing, they're just dividing by itself, something divided by itself equals 1. If this is equal to 1, I can just multiply it by whatever I want. Because when you multiply something, whoops, when you multiply something by 1, you don't change its value. So this right here equals 1. I'm just multiplying by 1. But I've done it in a specific way where I have a unit of days up top here and a unit of days on bottom here. So I can just cancel the days out. And so far that leaves me with 24 hours. I've converted 1 day into 24 hours if I just start multiplying everything I have here. 1 divided by 1 times 24 hours. So after hours, very good. So 1 hour is 60 minutes. And 1 minute is 60 seconds. So cancel out hours, cancel out minutes, and I'm left with the unit I want, 60 seconds. So now if I was just to throw this into a calculator, 1 times 24 divided by 1 times 60 divided by 1 times 60 divided by 1, and that'll tell you the seconds in a day. Thank you. And that's our answer. So when I do a conversion on the board, it's probably going to resemble this sort of a train setup. You don't have to replicate this on your shown work when you convert something on a test and you write your work down to show me. If you have a different method, that's fine. This is just how I do it. It's what my work is going to look like. And our next one here, we have a rectangular building lot measures 1 times 10 to the second feet by 1.5 times 10 to the second feet. I'm going to put a purple line here to separate our two problems from one another. So the x component of this is 100 times 10 to the second feet. Y is 1.50 times 10 to the second feet. What we would like to know this is what we know. These are the two things that we're given right now. We want to know the area of this plot. So we have a rectangular plot of land. We want to know its surface area in units of meters squared. Meters squared. So, good tactic for working any physics problem is to list what you know, what you don't know. Once you have these, figure out what sorts of conversions or formulas you have access to that contain these things to help get you to the answer you want. So, off the top of your head, what's the formula for the area of a rectangle? Right, length times width. We know the length of this rectangle, we know the width of the rectangle. So we can multiply these two things together in order to get that. So, our first formula, area equals, I'm just going to write that as x times y, length times width in two separate axes. Quick scientific notation question. 1.00 times 10 to the second power. What is this equal to? Very good. I'm just going to write in 100. And so what would this be equal to in standard? 150. Very good. So 100 times 150. That's going to give us 150, 15,000 something. What would our units here be? Very good, feet squared. We just multiplied feet by feet, so that has to be feet squared. Feet squared is a unit of area. So, that is our answer in feet squared. That is the area of the surface. We have found the area. So, that's basically the whole question. The problem is that it asks for us that information in meters squared. So even though we have the variable we want, we now have to convert the answer. So, how can we convert from feet squared to meters squared? Very good. So, instead of our conversion, we have 15,000 feet squared. Now we want to cancel out feet and leave ourselves with meters. Now, I have listed a conversion here between meters and feet. So 1 meter is 3.3 feet. If I put into our conversion down here, 3.3 feet over 1 meter. So again, those two things are equal to each other, so I'm really just multiplying by 1 here. I'm not changing the square footage of the object, I'm just changing what unit it's in. Arranging it like this will cancel, this feet here is on the bottom, this feet is in the numerator. So that should cancel out the feet, right? And leave us with meters squared? Almost. Almost.
It's feet squared, right?
Exactly. This is feet squared, which is technically a separate unit to feet. So if I only do this once, trying to use different colors where possible. If you only do this one time, you only cancel one of the feet. So if you just divide 15,000 by 3.3, your answer will be in units of feet times meters. You only put meters in once, and you only cancel out one of the feet squared. Yep, you just do it one more time. Which, just the way I'm going to set the train up, I just put it in one more time. That cancels out both feet and leaves us with meters times meters, which is meters squared. So, now you take 15,000 and divide it by 3.3 once, then you take that answer, divide it by 3.3 again. Now, who doesn't have a calculator yet?
I want it in my room.
Okay, honestly, I recommend once you get it, just letting it live in your backpack. Mine has been in there, I've had this longer than I've had this backpack, and it just lives at the bottom. I know exactly where to reach in and find it and fish it out. So, especially when it comes to like test time, just keep it in there, honestly. I know this may or may not be the only class where you use it, but it's handy to just have on hand. It is useful to have on hand. So, what do we have for our answer in meters squared?
1,377.
Very good.
41047 squared.
Very good. I'm not too bothered by sig figs in this particular class. If anyone remembers significant figures from other courses they've taken. My usual rule is try to include to the 100th place if you can. So, 100, I also have this quirk where I know what I'm supposed to say and a different word comes out, especially with numbers. So this is 1,377.41 meters squared. It's the same amount of space as this, we just change what unit it's in. And that's it. That's these two questions. I should not take the caps on these markers. And those are our first physics questions. Congratulations, you've done physics. You have examined the universe and measured something, or at least converted some of those measurements. We're just going to be doing that repeatedly with some more algebra and some bigger numbers. Cool? Okay. It's over half of the class period, and I've been talking a lot, so if anyone needs some water or to go to the bathroom, now's a good time. We'll give you guys a minute. I have a million emails that pop up every second that I can glance at. Pausing every so often because it lets the hot air exit this thing.
It's kind of cold in here.
The room is usually pretty cold on account of the fact there's no windows. When I first started working here, and when I started coming into my office to get things set up last summer of 2019, my office fan worked so well, too well. The AC in there was so cold, I actually couldn't sit in the room. It was like maybe 50 in there, and I had come in shorts because it was summer outside. So there was a solid day where I was camped out outside my office because it was just too cold to be in the room. So these things can be powerful when they're primed right, I know that much. Sadly, and we'll talk about more of this like partway through the semester, Air is a very good thermal insulator because when it gets heat, it keeps it. And I just have got a permanent little layer trap in here at all times. All right. Any questions? Anyone need anything? Okay. So, we've talked about how to do science. We've talked about measurements and units. Now we're going to begin looking at specifically some of the things that we measure and how we're going to calculate use some actual formulas and talk about the universe itself now. So, we live in a three-dimensional universe. That means that there are three different axes, three different physical directions that something's movement, that its location can be described with. Now, just because we have up to three, there are three dimensions. We're not going to talk about all three of them at once in this particular class because 3D math is kind of a headache. We're going to begin with one-dimensional motion. So, one dimension is just going to be back and forth in a straight line. This is like your x-axis. And I will now label it as such. So this is one dimension, forwards and backwards in a straight line. Now, what's interesting is this one dimension can represent two directions. You can go forwards or backwards on this line. Either way, you're still moving in the same dimension. So we can consider, if we consider this axis of the classroom to be the x-axis, I'm just walking back and forth one-dimensionally just along this one single linear axis. This is one of the three dimensions that make up our universe. Because in addition to being able to walk just this way, I could also turn 90 degrees and start walking this way if I wanted to. So that is one of the other dimensions. There are three of them. I can't really draw walking in this direction on the board, but this is usually the depth or z-axis. I could go forwards and backwards in this direction if I wanted to. Frustratingly, boards are 2D, so it's kind of hard to draw that third dimension. Instead, I'm just going to draw the y-axis, which would be if I was jumping up and down. I figure you've had math classes where you look at axis systems like these. So right now what I have drawn on the board is a 2D grid. So this is 2D, two-dimensional. All of any given point on this axis, on this graph, can be described in terms of how far it is in the x direction from its origin and how far it is from the y-axis from its origin. Any point in the universe you can describe this way. I can say that that projector is 3 meters this way, 4 meters this way, and 2 meters above where I am now, and that'll tell you, where it is in relation to me in each of our axes. So we live in three-dimensional space because we have x, y, and z. X, y, and z. In this class, we're only really going to look at x and y together at the same time. We're going to start with one dimension. We're only going to keep one dimension at a time to begin with. Eventually, we will move on to two. But I want you to be aware that the third dimension exists because it's important. We are three-dimensional beings in three-dimensional space. So, we're just going to begin with one dimension right now, moving just forwards and backwards in a straight line. Now, one-dimensional motion. There are three main components that we use to describe how something is moving. Those components are listed here. we have displacement, and if I was to simplify displacement, it would be length. It is distance. It is the distance between 2 points. So, this is going to be our first variable that we really focus on in this particular class. All of our variables are the things in our formulas that change and depend on what the problem is talking about. For every new variable I give you, I'm going to tell you what it is measured in, since we're using the metric system for the most part, we're going to measure displacement primarily in meters. We're going to use meters for the most part for how physically far apart two objects are. So, the unit for displacement is meters. The unit for displacement is meters. The variable for a unit for a particular concept is going to be what letter we represent it with in a formula. And there's really three common ones that might show up for displacement. If you're looking at a formula and the formula has a D, an X, or a Y, it's referring to displacement. So, for example, the formula that we put up on the board earlier, oh, hang on, we've had a few formulas up on the board total. So if these are physics formulas, this D right here represents displacement. But sometimes if I pull something from a different source, or sometimes in my own brain, because I've used a lot of different letters to describe displacement specifically, sometimes I might write delta X. And I would mean the same thing. I would use this to refer to displacement in the X-axis. I might use Y to refer to displacement in the Y-axis. Displacement is frustratingly the one that I use the most separate letters for, depending on the context. But if these are just your single variables, it's referring to displacement in the question. So, the variable is the letter that you will see in the formula. And if you are told, displacement is 10 meters, and you're using this formula, you could plug 10 meters in for this delta X. This delta X would represent the change in displacement for that question. If you know your displacement is 10, this is where it fits into the question. So for every variable I give you, I'm going to make sure you know the unit it's measured in and what its variable shortcut is in the formulas. Okay? All right. Now, displacement, we use that to talk about the physical distance between 2 points. So the displacement between myself and that wall is a certain length that we can physically measure. The displacement from one end of this stick to the other is 2 meters. So meters displacement is just a physical measurement of length for is how we're going to use it in this class. And in one axis, it's just the length between 2 points in a single direction. Now, the next one is velocity. And I know this is a term that you've all heard before. It does have a very specific definition as written up on the board. A measure of displacement over time. Its formula is V equals D over T. Is measured in meters per second. And its variable is in lowercase v for velocity. Now, velocity Velocity is defined as the change in displacement per unit time. If we were to simplify that concept, what would be the first thing you think to call it? Miles per hour is a unit of velocity, yes. So this is the metric unit that we will mostly use, meters per second. Miles per hour measures the same thing. They are both measures of velocity. You could say they're both measures of speed. It's just how fast something is moving. Meters per second, miles per hour, it's a unit of length over a unit of time. In order to have velocity or speed, you need to be moving, you need to move some distance in some amount of time. Right now, what's my velocity? 0. So looking at the formula for velocity, velocity is a change in location. So who is unfamiliar with the triangle appearing in math? Okay, so this is meant to be a Greek letter delta. And sometimes I know my handwriting is a little stinky. But if any of our formulas have a triangle in them, this is the Greek letter delta. You might see that on fraternities somewhere. Oh wait, you have tri-delts here, right? Is a sorority. I might get confused. Oh well. It is a Greek letter. It shows up in Greek life on various campuses. In math, it means change in. So if you put a delta in front of anything, it represents a change in that particular concept. So if you are moving, if you have a velocity, where you are is changing as a function of time. Me standing here right now, I have a fixed location, but that location isn't changing. So time is still passing. If we were to try to calculate my velocity right now, time is passing. Seconds are going by, so there is a number of seconds down here that we could look at. If we examined my location over time, we start a stopwatch and we just examine where I am. Time will still pass, but in that time, I'm not currently going anywhere. My change in displacement right now is 0. You could measure how far I'm standing from something, but my change in location is 0. I have no velocity. Now, meanwhile, if we try again, if I start walking and I hit the stopwatch, let's say I travel 10 meters to the end of the room, and it takes me 5 seconds to do that. I moved 10 meters in 5 seconds. What was my velocity? A little louder? 2. Velocity is the rate of movement. It is a rate, meaning two things are changing at once. One thing changes in relationship to another. Velocity is the rate of change of your location over time. If something has a velocity, its location has to be changing as the seconds elapse. So it's a rate. It is a rate of change. I think I'm actually going to skip ahead just a little bit. Okay. Right now, I only want you to focus on this top one. I'm skipping ahead so that we can do a velocity example, okay? We're just look at this top one for right now. We'll get to the others in a minute. So, this is a quick sample question. You drive at a velocity of 55 miles per hour for 23 minutes. So, first thing you do is read the question, determine what you know and what you don't know. We know the velocity is 55 miles per hour, and we move at that velocity for a time of 23 minutes. What we are asked for is our total displacement. How far did we travel in that amount of time? Is this how fast we were going? Every single hour, we would go 55 miles. So miles per hour, that literally just translates to, in an hour, going at this constant speed in a straight line, you'll travel 55 miles. Doesn't feel like that in rush hour traffic, but that's what it should mean. Our time, the amount of time we traveled at this velocity is 23 minutes. So how do we find how far we went in this amount of time?
Why don't you divide 60 by 23, or the other way around, and then looking forward.
Okay. Good instincts. For the sake of getting it in everyone's notes and for teaching good physics habits, we're going to start with the formula and we're going to get to that point. So, yes, your usual steps for tackling a physics question. Figure out what you know, figure out what you want, figure out what formulas have all of these in them. We've only really talked about one or two formulas so far. So we know velocity, we know time, we want displacement. We have one formula that very handily has all three of those in it. So we're going to use that one. Velocity is equal to change in location over change in time. So if we just start plugging our numbers in, 55 miles per hour is equal to, we want delta t, so we're going to leave that as a blank variable. This is going to be what we solve for. And then divided by time, 23 minutes. Okay. So what do we do next? Okay. So we've got d over 23. We want d equals something by itself. We want d by itself. So we're beginning our algebra practice now. If we want to get d by itself, what do we have to do to both sides of the equation?
Multiply 23.
Multiply. Very good. I'm going to put in the full step for right now. I know I tend to skip things, but I'm going to make sure I write everything out for the time being. So right now we're multiplying both sides by 23 minutes. That's going to have the effect of canceling this 23 over here. So really we just sort of multiply by 1 again. This divided by this, they're just going to cancel. And all we've done is had the effect of moving the 23 to the other side. So now we have d equals 23 times 55. Is that our answer? Why is that not our answer?
In different units.
The units don't match. This is time in minutes. This is miles per hour. We need to convert something here so that our units of time cancel and we're just left with a unit of distance. Because our goal is to get displacement. The only unit we want left over here is miles. I'm going to rewrite this MPH for a second because this is technically miles over hours. I know in the US we like to write MPH, but in terms of the actual variables at play, you're dividing the miles you travel by the hours it took you to travel them. So, ideally, we have time on the bottom here, we're multiplying by time, that would cancel the time units and leave us with miles. Unfortunately, they're not the same time unit. This is minutes, this is hours. So we have to convert one of them so that they match and cancel out. What seems the most straightforward to convert? Okay, we can convert this minutes to hours, and then it'll cancel out with this hours. So, we come over here, we have 23 minutes. We want to get rid of minutes and leave ourselves with hours. So, there are 60 minutes in 1 hour, and if I write the orientation like this, again, these two things are equal to one another, which means I'm really just multiplying 23 by 1. I'm not changing its value, I'm just changing its units. If I stack the fraction like this, that's going to cancel out the minutes and leave us only with hours. Everyone see that? And that will just tell us the amount of hours that 23 minutes is. Very good. So 23 minutes is equal to 0.383 repeating hours. This little line here, when you put a line like this, a flat line over a number, it means repeating. So my calculator is telling me 0.383333333 because it's sort of like one of those weird 1/3 scenarios where it's not a very clean fraction break. It's not super important to write that down on your page, but if you do see that line there, it means whatever number that line is over repeats forever. Just to make sure that notation is clear. So this is the hours. This is the hours version of 23 minutes. And that makes sense. This is less than an hour, so we have a fraction of an hour. It hasn't been a whole hour. So this is a good conversion. It makes logical sense. So we can replace 23 minutes with this amount of hours. And so now we have 0.383 hours times 55 miles per hour equals our displacement. Multiplying these two things together, we have hours in the numerator here, hours in the denominator here. So we've met our goal from before. These hours are going to cancel. That leaves us only with units of miles, which is what we want. We want our displacement. Displacement talks about length. Miles is a unit of length. We've gotten the right unit. We're getting the right answer. So now we just multiply 0.383 by 55. What does that give us?
1.65.
Very good. Okay. Sorry, there's some slight fraction rounding errors with calculators here. All right, your answer might be slightly different based on fractions and calculator rounding and stuff. As long as it begins with 21.0, you're good. Okay? If it's slightly different to this, but mostly the same, if it's at least 21 point, you're fine. I'm lenient with the way the calculators work. They're all, these machines, like we call them smartphones, smart calculators, they're really dumb, level with you. They make mistakes. So as long as your answer at least is 21.0, we're good. This is the miles that we traveled in that amount of time, and that's physics. You did it. Every other problem is going to be exactly these same kinds of steps, exactly this same logic and process. Just over time, things will get, the formulas will get bigger, some of the numbers will definitely get bigger, but it's the same method the whole semester. It's all stuff you've done before. We will pick up these examples next time because these start dealing with acceleration in addition to displacement and velocity. You're nearing the end of the period. So, as a reminder, we don't have labs this week, so the H lecture's in a weird spot because if you say on this particular day if you have the Thursday lab, you wait 15 minutes after class and then you're back into the lab. I'm fine if in that time you need to go take a break or get a snack or something, you don't need to stick around. But you're welcome to stick around if that's the easiest thing to do. But again, no labs this week. Get acclimated, the class is starting. We'll begin the actual assignments next week. Does anyone have any questions about anything before we break for today? Okay. This recording will be up as soon as upload speeds allow it to be. I'll try to get these notes onto the Brightspace page, and just as a refresher, I'm going to, if you click on, the Unit 1 tab, video lecture links will be in that tab. I will be putting these notes as a sub-tab down here, like how these documents are sub-tabs in the syllabus category. So if you want specifically the notes, check there for that. Email me any questions you have. Make sure you can get in the sapling. Assignments will be posted soon to be due in the coming weeks, not this week. Go ahead and get in so you can get started as soon as we can. Thank you all, and if you've got no questions, please have a wonderful day and a wonderful weekend. I won't see you until Tuesday, probably. Not due this week. Yeah, I'm probably going to start putting them up to be accessed, but they won't be due.
I have one question for you about